Welcome to another example, a beam with an inclined roller. The supports are a hinge at A and a roller at B inclined to the horizontal with angle theta equals 45 degrees. We have a distributed load of 2 tons per meter run acting between C and B, and a concentrated moment of 4 meter tons at D.
To consider our reaction, let's have a resultant of the distributed load, which will be the intensity multiplied by the length on which the load is distributed, 2 by 8. And the point of application of the resultant is in the middle of CB. The hinge carries two reactions XA and YA, while the roller carries one reaction RB, which is perpendicular to the direction in which the motion of the roller is allowed. The analysis of RB is RB sine and RB cosine the angle as shown in the red forces. To get the reaction YA, we consider moments about B. We consider 2 by 8 multiplied by the arm of this force 4 meters to be a moment about B. So it will really rotate in this sense, counterclockwise. Therefore, all moments rotating about B in the counterclockwise will be considered positive and vice versa. So we have YA rotating clockwise about B, it is a negative moment, 4 rotating about B in a negative sense also. This makes YA to be 10 tons and plotted on our diagram. To get the reaction at B, consider forces in the vertical or the y direction to be 0. You can choose any direction to be a positive direction, and the opposite will be a negative direction. This is applicable because the equation in the end is equal to 0. So 2 by 8 is taken as a positive force, therefore 10 will be a negative force and RB sine will be a negative force. This gives RB 8.49 and plotted on our diagram. The analysis of this 8.49 in the horizontal and the vertical directions will be 6 tons for each and plotted on our diagram again. Finally, to compute XA, take sigma forces in the x direction to be equal to 0. We have XA and an opposite 6 tons, giving XA to be 6 tons. Now we are ready to plot all our internal forces. Normal force. Please note that the normal force from C to A is 0 because this 6 tons is applied starting from A. So we have NA left equals 0 and NA right equals minus 6 tons. Please recall that while plotting our normal forces, we are searching for all forces in the direction of the center line. And it is clear that at A, 6 tons is a compression force and therefore will be plotted below the center line of the beam. No other normal forces are met until we reach B. And the closure here is this 6 tons, the red 6 tons, acting in an opposite direction, so we will rise and we will have a closed diagram which indicates that we computed all forces in the x direction correctly. Shear force diagram. To compute our shear, we point out two facts. The first, A has two values of shear, one QA left and another one QA right, with a difference of 10 tons. This is because of the existence of the concentrated shear YA equal 10 tons. The other fact, that you can never really draw the shear forces with the resultant 2 by 8. We should divide this resultant into two parts. One, expressing the distributed load from C to A, and the resultant is 2 by 2. Another one, expressing the resultant of the distributed load from A to B, and the value is 2 by 6. Now we start drawing. We have shear at C equals 0, and from C to A we expect a shear of the first order drawn as an inclined line heading in the direction of the applied load downwards. So we have QA left equals minus 2 by 2, minus 4 tons, and plotted on our diagram. To go to the right of A, we have the last computed shear and we add the value of the concentrated shear 10, giving a net shear of 6 tons positive. From A to B, to reach B, we apply the 2 by 6 tons to the last computed shear, respecting the sign convention. And therefore, we have a net of minus 6 tons shear. The diagram is closed by the virtue of these 6 tons drawn in red. Our shear is plotted. To plot our bending moment diagram, we have a zero moment at C, and to compute moments at A, we have this part of the distributed here acting between C and A. So we have 2 by 2 multiplied by the arm, 1 meter, making a moment of minus 4 meter ton to be plotted above the center line. Now we need to compute the moment at D left. We recall that we have a moment at the right section of D and another one at the left section of D due to the concentrated moment 4 meter tons applied at D. Considering MD left, we can simply take the effect of 2 by 2 multiplied by the arm and 2 by 2 multiplied by this arm, and the effect of the green 10 tons multiplied by its arm to reach D. Or simply, we consider the distributed load as written in this equation, a resultant from C to D, making a resultant of 2 by 4 multiplied by the arm, which is 2 meters to reach D. The moment here has a negative sign as the tail of the force causing the moment is upwards. And we have a positive moment created by YA equals 10 tons by this 10 tons multiplied by the arm, 2 meters, making a total of positive 4 meter tons to be applied below the center line of the beam. To compute MD right, we simply add the effect of the 4 meter ton concentrated and applied at D. For a better explanation, we have our D here with the applied 4 meter tons. We settle this moment at the left as we started computed from the left-hand side, and therefore we conclude that the tail is below the center line of the moment, and we add this moment. So we have 4 plus another 4 concentrated equals 8 meter ton, and we plot it on our diagram. At B, there is a 0 moment. Please note that for a hinge support and roller support acting at the end of the beam, we have 0 moments. But if we have an overhanging part before our support, it carries a moment. The parabolic drops, one for the part CA equal 1 meter ton, another for the part AD equals 1 meter ton, and the last one for the part DB equals 4 meter tons. Now consider we want to search for the maximum moment acting on the beam CB. Let's consider that this moment acts at a point X from B. So we have the distributed load at the part X equals 2 by X. And our shear at the X section here will be 6 tons and the 2 by 6. Consider that we are starting to consider the shear from our right hand side, and therefore we will inverse all our signs. The 6 tons heading upwards will have a negative sign, and the 2 by X heading downwards will have a positive sign. Another important notation is that the maximum moment occurs at 0 shear. This is because the moment is the integration of shear. This gives X equals 3 meters, which means that we have our maximum moment at 3 meters from B and computed as such. 6 by 3 minus 2 by 3 by 3 over 2, which is the arm of this force, giving a total of plus 9 meter tons. This concludes with our example.